Okay, perfect. So good morning everyone. My name is Mauricio and today I'm going to give a presentation about a triple arc incision to correct presbyopia and myopia. Okay, so the main topic of this presentation is the cornea biomechanics. And throughout the presentation we're going to see that we propose a new surgery model for the cornea and we are going to present how we validate the results. So let's move on. Here's the outline. We have four major parts. The first one is the introduction, then I'm going to move out the methods, then the results and the discussion, and finally to the conclusions of our investigation. So first of all, in the introduction, let's talk about the cornea. So here I have a global picture of the ocular globe, and I have here highlighted the cornea. So the cornea is like a hemispherical shell structure in the top of the eye. And it has three major functions. The first one is to protect the inner contents of the eye, so what is here. The second one is to maintain the shape of the eye. And the third function, which is the most important one, is to refract light. Why is that? Because the cornea has to refract the light beams which come to the eye and refract them to the retina right here. So each light beam which goes here must be refracted to the retina. If not, we will have problems and diseases. So that's the main function of the cornea. Okay, let's see something about refractive surgery simulation. So here we have a normal eye, a healthy cornea, and here we have the light beams which are refracted to here the retina. So the focus of the light beams is just above the retina, so that is how it should be. However, we have some refractive errors which are simply diseases which are undesired, and we have a lot of examples. For example, myopia, presbyopia, hyperopia, and so on. In this case, the cornea is a little bit curved. That means that the curvature of the cornea is increased, so it's not like a hemispherical shell structure, but a little bit curved. This causes that the focus of light beams is just before the retina, not here, but just before. And that's a very huge problem. The other problem, which is most like the contrary one, is the presbyopia, which means that the cornea is not curved but flattered. That means the contrary of curved. So the focus of light beams is just after the retina, right? So these are two very common refractive errors, myopia and presbyopia. Presbyopia is really affects the lowest part of the cornea. Sorry, here, the lowest part. And we can see that while reading. For example, you see your grandparents, they have this, some of the grandparents or older people, they have this disease, and it manifests while reading. For example, they have the book here, and in order to read it good, they make it farther, right? So it's how this disease manifests. Okay, let's see some things. As we said, refractive error is undesired changes in corneal curvature. As I say, this myopia here is caused by a curving on the cornea. So what we must do is to flatten the cornea, so reduce the curvature in the cornea right here. On the contrary, in presbyopia, the thing is here we have a really flattened cornea. So what we must do is to curve the cornea in order to the focus to go here right above the retina. Good, so our main objective is to formulate and simulate a new refractive surgery. So the state of the art is that, okay, first of all, the refractive surgery is the surgery that corrects these refractive errors, right, these diseases. But the thing is that until the moment, each surgery rather flattens or rather curves. So each surgery provides just one effect, or curving or flattening. So our main purpose is to design, to formulate a new surgery with a multiple effect. So that means that the surgery will also flatten as well as curve the cornea. And with that in mind, we could correct, for example, two diseases simultaneously. So that is our main objective. Okay? Good. We move to the methods section. So that's the surgery we are proposing. We are proposing a triple arc incision. Imagine that's the human cornea. Looking at above, if we had Imagine we have here the nose and the other eye. Okay, so we are looking at the person right in front of it. Right in front of it. And the cornea is, okay, here right in front of it, and we have 3 incisions. They are arched, they are symmetrical, and we have 4 different parameters. We are varying this radius, we are varying this arch, we are varying also the depth of the incision and the width of the incision. So that's a really new idea. Other surgeries, for example, are with 2 lines, 2 incisions in a parallel incisions, and that's the way how it's done. So this is our main objective. That's the surgery we are trying to simulate. Good. What we want to do is, okay, before that, these are the incisions, and inside the incisions, this zone is called the optical zone, and that zone is the most important subject of investigation in our research. So we want here to have changes in curvature in order to apply this surgery to patients. Okay, let's move on. So I will go very quickly through the major steps in the simulation of the surgery. This simulation is done in a very specific and technical engineering software, and it has mainly 3 steps. The first step is called the geometry generation. So what we are doing is we are doing a geometry of the human cornea. The parametrization, the parameters are really well known in the literature. So we take this shaded area and we rotate it, and we have here a hemispherical shell structure. With our geometry, we move on to the second step, which is the boundary conditions. What do we do here in the boundary conditions? We apply some conditions in order to validate our model, or in order to apply real conditions to what is happening in the cornea. So what we have here in the cornea is, here on the internal area, we have a pressure. That is because the eye, inside the eye, we have a lot of intraocular fluids, and that is like a balloon. The balloon has an internal pressure. So that kind of pressure is being applied to the human cornea. Also, that's the first condition, and the second condition is a support, a roller support on the surroundings of the human cornea. These 2 are the most important conditions. We apply them into our software, and then we proceed to the third step, which is the mesh. So in order to solve the model, we must solve lots of equations, and in order to solve them in the entire cornea, we divide the cornea into small pieces. So we have here very small pieces. That's called the mesh, and each point is called a node. So in each node, we are solving lots of equations, physics equations. That's the third step of our procedure. When the entire procedure is already done in our simulation, we can see what is the curvature change after this triple arc incision. So we move on to the results and discussion. Okay, here I am plotting 2 different dioptric maps. That's the cornea curvature without the surgery, and that's the cornea curvature with the surgery. We see different things. For example, here we see 3 incisions, which are the incisions that we are performing. Inside the incisions, this is the optical zone, which is the most important region we are investigating, and the hot colors, not before. The hot colors like red and orange represent curving, represent a change, an increase in curvature. And the cold colors, like this one, like the blue and the dark blue, represent flattening. And as I said before, in order to correct myopia, we need to flatten it. It means we need to have here blue zones, as we have it here, here, and here. And in order to correct presbyopia, we need curved regions, which are hot regions. And we see that with the surgery, here we have as well as hot regions, curved regions, and as well as flattening regions. So the previous surgeries, they only account for one change here, rather flattening or curving. But we proposed and we obtained a multiple effect. That's right. We also may compare our simulation results with clinical cases. So here we found this clinical case, we investigated which was the incision geometry, and we simulated with our program. We simulated this clinical case with our program. So we see, for example, different things. The most important region in order to correct presbyopia is this triangle here. And we need to have curvature, it means red zones, in the both regions. And that's really well predicted with our model. However, here in the clinical case we have flattening regions, these blue ones and these green ones. And they are not predicted by our model. So we have one major reason for that. And is that these incisions were performed by hand. And the incision geometry is not very accurate. So we are not able to just simply compare our perfectly simulation with the incision which was performed by hand. But the major tendency, which is the increase in curvature here and here, is really well predicted, and that's really a satisfactory result. With that, we move to the conclusions. So the first conclusion is that both curving and flattening simultaneously occur in the optical zone, which is our main objective, which is really new in the refractive surgery simulation. The second conclusion is that the incision geometry influences on curving and flattening. We had 4 geometrical patterns in the incision geometry. We investigated that if we do a very small incision, the change in curvature is really different as if we do a very large incision. So this is really well. The third conclusion is that the simulation tendency, as we saw, agrees really well with the clinical cases. Still, however, we must improve our mechanical model in order to validate better our results. And finally, the entire project will be of great help in order to design a personalized surgery for each patient. So taking into account each patient's cornea geometry, taking into account which incision will be better, and so on. And that's the end of my presentation. Thank you.
I have 2 questions. Is there time?
Yeah, fine.
Okay. So the first one is that how do you work with doctors here? I mean, where is the doctor's part in this?
Right, that's a
And
good
secondly,
question.
the second thing is like if you have already had the surgery, the LASIK surgery, can you do? I mean, it's supposed to be that one also. You can do also that one, or is already done?
Okay. So for the first question, we are working with a 3-group member. We are working with a professor of civil engineering, and the third author is an ophthalmologist. He works in the Instituto Barraquer. You know it. So we are 3 co-authors, and he almost like guided through the entire research.
Okay.
So of course he's doing all those tests in animals and so on. And for the second, I could not say. For the second question, we should ask the ophthalmologist.
Okay, thank you.